scholars, today we're going to talk about graphical transformations as well as how to represent these transformations using function notation in sort of a formal way. And as a starting place, you can imagine if you just have your xy plane, and let's say we wanted to graph some function. We'll just do a quadratic, right? So we can call this y equals f of x. So as sort of a general starting point, if we wanted to think about what is a transformation, well, it's basically saying, let's take this graph, this entire graph, and we can do things to this graph. For example, we could shift this entire graph to the left. That's one shift that we could do. We could transform it by shifting it to the left. We could shift the entire graph up, right? That's another way that we could move this graph. We could actually reflect this graph over, let's say, the x-axis, right? If we reflected it, it would look something like this, right? And we could also reflect it across the y-axis, and it would look actually pretty similar. It looks something like that, right? And so basically, this is just all to say that when you think about a transformation, it's really helpful to think about taking the entire graph as if it's an object, as if it's something that you can just pick up and move around, right? We could even, if we wanted to, we could even take this graph and bend it, right? That's another transformation. So instead of it being so narrow, we could even bend it, make it nice and wide, or bend it such that we actually flip it, right? These are all possible ways that we could sort of either statically move this graph around the xy plane, or as if we have a pair of pliers, right, here and here, we could actually pull it apart, bend graphs, right? We can do all these things to graphs. So let's take a look at a couple of examples. Example number 1. If f of x equals the quantity x plus 3 squared, write the function rules described below explicitly. So we want to write out g of x and h of x. These are two functions that we define in terms of how they relate to the function f of x. So let's start with g of x. We know that g of x is equal to negative f of x. So is equal to negative, and let's just plug in what f of x is, right? If this is my f of x, right, I know that f of x right here is the quantity x plus 3 squared. So g of x, we can write it as g of x is just negative x plus 3, that quantity squared. So this is just a simple substitution, right? Okay. What about h of x? Now h of x looks pretty similar to g of x, right? They both have an f, they have an x, they have parentheses, and they have a negative, right? So they look pretty similar. However, it's a very different function. H of x is telling us, so let's start writing it. So h of x is saying that it's exactly the same as f of x. So let's write down f of x. F of x is x plus 3 quantity squared. Only instead of here, my input was x, and so my output was x, right? Here, my input is a negative x. So in other words, wherever initially in f of x I saw an x, I want to actually make it a negative x, okay? So h of x explicitly is written as negative x plus 3 quantity squared, which actually we could also write that, right, just by flipping it around as 3 minus x squared. This is another way of writing that. So g of x and h of x are very different functions. Let's take a look at graphically, the graphical representation. So we'll just do a quick sketch here. Okay, so here's my xy plane, here's my x, there's my y. If I wanted to graph x plus 3 squared, just graph f, right? F of x. That's going to be there's a parent graph of x squared, so it's going to be a quadratic function opening up, and it's going to be actually shifted 3 units to the left. So this point right here would be negative 3, and this is where my vertex is. So as a rough graph, here is my graph of f of x. Okay. How do I graph g? Okay, so g is telling me that whatever f values I had, right, I want to make them negative. So if I had positive f values, I want to make it negative. That's what this negative is doing right here for me, right? So for example, here in the graph of f, let's say I had this point, right? And this point is a positive y value, right? It's a positive function value. I actually want to make that point negative in my graph of g, right? This point is just 0, so I could make it negative 0, it doesn't do anything. This point was positive, I want to make it negative. This point was positive, I want to make it negative. Every point on this graph we are changing the sign, right? The sign, the sign of that point of the function value. And when you put them all together, right? Roughly you get through these points. It's essentially the graph of g of x is a reflection of f of x over the x-axis, right? It's as if this is a mirror and we're taking this entire graph and we're just sort of flipping it over, right, to graph g of x. Okay, so that's nice. This is a interesting observation. So when you have a function that is just, you're graphing the negative of the function, you're basically saying any function value you got, flip the sign, right? If it was positive, it's now negative. If it was negative, it would become positive, right? Because a negative of a negative is a positive, okay? So this right here is g of x, just to make a note of it, is a reflection across the x-axis. Okay, so let's take a look at now h of x. Now h of x is saying something a little bit different, right? It's saying that the inputs now are going to change signs, right? Instead of just saying f of x, we want to do f of negative x, right? So it used to be that I would plug in f of 2 and I would get some answer, right? But now I'm going to plug in f of negative 2, okay? So what does it look like on a graph for the x values to be changing signs? Okay, so let's actually do it in blue. So here we're saying that it used to be the point negative 3, 0 was on the graph of f of x, right? But I want to change the sign of that x value. So instead of negative 3, 0 being on it, right, positive 3, 0 is going to be on my graph, my new graph of h of x. And we can do a similar thing here. This was here, let's say this is the x value of negative 2. It got me this point right here, right? Whatever point that is, that was my output. But now, positive 2 is going to get me that same output. So positive 2 now is going to get me that same output here, right? And we can even go further, right? We can say that now this point used to be maybe negative 4, right? Got me that point, but now it's going to be, right, positive 4. And we can sort of see where this is going. We can map these functions, these graphs, and end up with a graph of roughly, so not the best quadratics, but end up with a graph of h of x. Now h of x is a reflection, now we can see, across the y-axis, right? Every point here, it's like you took this whole graph and sort of like flipped it around the y-axis and plopped it here. So we can record that. We can say that when I'm changing the sign of the input here, right? That's the only difference between f of x and h of x is the sign of the input. It's saying all the function values where you inputted negative numbers, you got to input positive numbers to get those same values, and vice versa, right? You could go in the opposite direction as well. So this is showing us a reflection across the y-axis, okay? Okay, let's take a look at a couple more examples. Example number 2. If the function t of h gives the number of taxi drivers on the street h hours after midnight, then let's interpret these statements using function notation. What do the following mean? Okay, so let's start with this one, t of h plus 5. Well, we know that t of h is the number of taxi drivers, right? So this is a number of drivers, okay? So if I'm adding 5 to the number of drivers, we can interpret this as 5 more drivers, right, than the number of drivers on the streets h hours after midnight. So in other words, if there were 47 drivers on the street h hours after midnight, this expression right here is telling us that there are 52. Right? This is the expression to represent 52 drivers because it's 5 more than those 47. Okay, let's take a look at this expression now. And this one, it looks very similar again, but it's actually quite different interpretation. So we'll do it in a different color. T of h plus 5. Okay, well, we know that this is a function that takes as its input, right, the number of hours after midnight. Now here we are inputting h plus 5, okay? And so this h plus 5 is telling us h hours after midnight plus another 5 hours, right? After midnight, right? So this right here is telling us a number of hours. This is telling us the number of hours, as opposed to T of H is telling us the number of drivers, right? So here, this input is telling us the number of hours. So T of this input is another way of saying that this is the number of drivers, right, on the street, H plus 5 hours after midnight, okay? So in this case, the after midnight, in this case, the 5 is referring to an additional number of hours after midnight, whereas in our first case, the 5 is referring to an additional number of drivers. Okay, so you see there's a little bit of a large distinction between these two expressions written in function notation. Okay, let's take a look at one more example. Example number 3. Sketch the graph of f of x equals negative 1/2 times the quantity x plus 3 squared minus 2. This looks very complicated. There's a coefficient there, a negative fraction, there's a plus 3 and a minus 2, there's a squared. It'd be really tricky to actually graph this using a function table, right? If you plug in x equals 1, and then calculate x equals 2, right? You could do it, but it would take some time. So let's actually reason through this using the idea of transformations, graphical transformations. If I take away all of the coefficient here and adding the 3 and the minus 2, this thing is kind of, it looks like x squared, right? This is some sort of transformation of the graph, right? The quadratic x squared. There's a squared there, a squared there. So we can call this a parent function. And basically, let's graph this f of x sort of by starting with the parent function, y equals x squared, which again I can sketch pretty easily, right? Now again, this is a sketch, it's not perfect. Of course, these points aren't actually gonna line up perfectly, but we're just sketching, okay? So this is the parent function, y equals x squared, and let's start transforming this in a few different ways. Okay, so let's start with the coefficient here. So I have a negative 1/2. What does that do? What is a negative 1/2 going to do to this parent function? So here's my parent function, x squared, and I want to say, what if I have a negative 1/2 in here? Well, so first off, the negative is telling me that every where I used to have a positive function value, I want to make it negative, right? I want to change the sign of the function value, right? So for example, here I used to have this is actually the 0.11 over here, and so it's actually going to be down here, right? Here I used to have the 0.11, it's actually going to be down here. And this negative is really, again, like we saw earlier, reflecting across the x-axis, okay? So we know that this whole thing is going to be somehow reflected somewhat, right, across the x-axis, but let's actually keep going and ask ourselves, what does the 1/2 do? So the 1/2 as a coefficient is actually a bending coefficient. It's actually making this graph wider, right? So not only are we reflecting this graph off the x-axis, but we're actually going to make it a little wider. And we may ask, well, why does it do that, right? So again, this is our vertexes are still 0, 0. Why would this 1/2 make it wider? Well, it's as if we're saying that any function value you get, let's say I do some math and I get that x squared, right, is like 10. Okay, fine. So first off, the negative is telling me, well, now actually what used to be positive 10 is going to be a negative 10. And the 1/2 is saying, well, actually, it's only going to be half of that. It's going to be negative 5, right? So if I used to have input that gave me negative 10, now that new input is actually just going to give me a negative 5. And so that has the effect of making this graph a little wider. Okay, so let's keep going. What do we do about this plus 3? So I got a plus 3 here. And so instead of x squared, right, we actually have an x plus 3, that whole quantity squared. Okay, so what is that going to do to the graph? And so a lot of people will say, well, it's a plus 3, so it's probably going to take the graph and shift it 3 units to the right, because plus is positive, right? And this is the positive direction in the x-axis. So it's actually a little bit different, and we can reason about it as follows. In the original parent function, when I put in x equals 0, I got out y equals 0. The function value was 0, right? And that has to do with the fact that on our original parent function, right, in black, here's the point 0, 0, okay? In this function, you want to think, what do I have to plug in for x in order to get out that same y value of 0, that same function value? What value of x would do that for me? And the answer is x equals -3, because -3 plus 3 equals 0. So if I want to get out that same 0 value, right, I got to have an x value of -3. So this point that's on my purple graph, right, but it's on both graphs, actually gets shifted over 3 units. It becomes this point. And where the 1 point goes, the entire graph, the entire purple graph will follow, okay? So this right here, plus 3, is shifting us 3 units to the left, and we're almost done. All we have left to do is do a -2 here. So let's do a -2 right here. And a -2 is just saying, yeah, you did all that stuff, and whatever you do, whatever answer you get, subtract 2, right? Change the function value, the y value, decrease it by 2. So we can do that pretty easily. Just take, if we can, again, think about this 1 point. If I decrease it by 2, it's down here, right? So that's a -2 there. So we shifted 3 to the left and 2 down, and where that 1 point goes, the entire graph will follow, right? So it'll look something, so not the best sketch in the world, but it will look something like this. So this is going to be my graph, the final blue one of, or here I'll do it in a different color, just do it in black. This is going to be my graph of y equals f of x, is this blue graph right here, okay? So again, just to recap, we started with a graph y equals x squared. We flipped it because there was a negative sign. We made it wider because there's a coefficient of 1/2. We shifted it 3 units to the left because it's x plus 3. And when you have that whole quantity, x plus 3 squared, that's a shift of 3 to the left. We reasoned about that. And we shifted it 2 units down because there was a -2 at the end. And so that's how you use transformations to graph sort of ugly looking functions. Have a great week.